very excited. I've never been to. Oh, cool. Okay. Yeah, I've never been to Madison before, so this is really fun. But it's such a beautiful city. I had cheese curds for the first time, which is amazing. I don't know where that's been. Yeah, so today I'm excited to be presenting some work that, as Yelena said, is in the intersection of economics and computer science. It's like pretty close to an area that keeps me up at night, which is this problem of where do metrics come from? Where maybe metrics in, I know this is an optimization seminar, you might think of something like an optimization objective, right, or a constraint. But here we take an economics lens on this and really try to understand, well, where do these objects come from in the first place? And I'm going to be presenting joint work with Mike Jordan, Katrina Leggett, and Justin McAfee. Yeah, so let's dive right in here. So today I'm going to be focusing on this object, this concept of metrics, which are, wherever you look, metrics are at the core of operations in organizations and in almost any organization or computational system that you can think of. Today, when I say metric, I'm going to mean a quantitative indicator of the value or difficulty of some task, which often determines the reward of some agent completing the task. So that agent could be a human agent. It could also be a computational system. Let me give some examples here. So in business operations, for instance, a metric for productivity of a software engineer could be the number of lines of code written by that software engineer. A metric for if you're running a research organization, or productivity of a researcher could be the number of NeurIPS papers that person published. We see metrics they're pretty core to operation policy as well, right? So we have different kinds of quality metrics for programs that are put out in the public sector. You could have, say, disease rates after implementing a public vaccination program. You'd have to look at, say, rates of transitioning into permanent housing for a homelessness service program, right? And I'm sure many of folks here are probably familiar with AI development and evaluation, or even just online platforms and systems in general. We have metrics, especially in AI development. There's benchmarks and new metrics for AI capabilities that are coming out every day. For example, say, folks here may be familiar with, say, an MMLU score for measuring an LLM's ability to answer multiple choice questions. We also have measures being developed for, say, LLM AI safety. A recent example of this is this ML Commons AI roommate score for measuring. It basically gives a grade, a letter grade for the safety of an AI system. So these metrics are everywhere. They're core to so many different operational systems. But I think for anyone who's really familiar with any of these given domains or any of these particular systems, I think we all know that these metrics, whatever quantitative indicators we have, definitely don't tell the whole story, right? As researchers, we know that the number of NeurIPS papers that a person publishes is only as at best an imperfect proxy of one's impact as a researcher, right? And yet we still see these measures everywhere. I mean, this is what can be measured. It is what is measured, and it's what kind of they still influence a lot of decisions in a lot of these systems. And sometimes, when you're in public policy, what else might you have to work with? Right? So this kind of leads to the question that has been driving a lot of my recent kind of thinking in this intersection of CS and economics is, well, what is this fundamental problem that the evaluator is facing when they are trying to develop metrics for either optimization or just to monitor a system that they have, right? So, and I'm going to argue today that there is a fundamental information problem here that the evaluators face, which is that, well, there's a question that they deal with, which is, well, of course, they care about how to collect and how to process the data that they have. But there's still this big question that I think we don't really quite know how to grapple with, which is what metrics should they be collecting in the first place, right? If it's not number of NERPS papers for researchers, what should we be measuring? So I will think of this like problem of, well, how do you collect and process data as maybe a problem of dealing with known unknowns, right? You know what you need, we just need, and we've made like a lot of really great progress in this area.
So, I mean, do we really need to collect or process the data? It's all somewhere out there online. And then rather than getting metrics, we could just say, hey, I have a question I want to answer. And then we can just go out and harvest whatever information we need to answer the question, rather than taking the raw data converting to metrics, then using that to answer questions, if you get my meaning.
I think so. So you're saying like I have a question about a system that I want to.
Yeah, like I want to know how good of a researcher is Kang Wook. Now I could have distilled it down to his H index or whatever other metrics, or I could just leave it as an open-ended question and take all information I can find about Kang Wook and then make my decision about how good of a researcher he is, without ever kind of going through this intermediate step of metrics.
Right. Yeah. So in fact, I think the kind of model that you're describing is something closer to what I'm envisioning for like, right? Because like we see metrics in this intermediate step being done in so many systems, but actually like, in practice, what if we could have something more open-ended like that? And still, even in that open-ended setting, there's still this question of like, well, where are you going to get you've kind of like opened the question, but then where will that information come from? Like who's going to tell you what to measure?
Yeah.
And I think that's actually the kind of focus of that's exactly like the question that I'm wanting to get closer to answering here, right?
Yeah.
Which is this problem of, well, yeah, like what should we be measuring? Say you do open the question of how do we evaluate this person? Well, now you're dealing with an issue of something that's an unknown to the evaluator, right? It's not that you know exactly what data you want to collect and you want to, all that matters is to like, get some statistical estimator and something like that. But it's more like I'm opening this world to how do I deal with the existence of these kinds of unknowns, right? So let me give like kind of a topical example here that might, in like this kind of AI evaluation space. Recently, there have been these like AI safety institutes that have been popping up all over the world. Many countries have been creating these, and a big concern or a big like goal that these AI safety institutes have had is trying to develop ways to measure or audit for safety of different AI systems. But like I use the word safety a lot here, and I think they use the word safety a lot. But there's still the question of, well, what do you really mean by that, right? Like what measure of safety is actually relevant, is actually important to people. These regulators have the power to mandate the collection, any kind of measure that they think of, but the open challenge here is, well, they don't know how to measure safety in the first place, right? So today, I've like kind of opened a can of worms here, right? I've opened this challenge, but what can we do, right? It seems like a really big problem space. Well, today I'm going to be discussing and kind of exploring a potential class of solutions here, which is, well, okay, maybe the specific evaluator might know exactly what metrics to like mandate collection of, but maybe that answer exists somewhere in the world, somewhere in the system of people with knowledge that is asymmetric. So maybe closer to the idea that you mentioned, where like, and who might that be? Well, maybe it could be lots of different people, but today the type of proposal that I'm going to be focused on is, well, maybe the evaluated agent could be somebody who has better information about how to measure their own performance. So what do I mean by an evaluated agent? Well, it could be that like maybe you as the researcher might like maybe like the university higher ups at the university might not know how to evaluate me, but maybe me as a researcher in my own field, I might know what is a better measure for my specific area, right? Or in the kind of AI evaluation example, it could be the companies that are developing the models, right? One kind of, but if we're going to consider this class of solutions, though, there's this core question that shows up here that we need to be able to understand in order to to consider that set of solutions, which is, well, when would an agent actually want to share a metric that is previously unknown to an evaluator? After all, it's going to come around and affect them in some way, right? Yeah.
But there's also this question of like what the evaluator, like what the bigger question the evaluator is focusing on versus whether that question is in like, especially for in economics, like businesses, right? Like there is question of like whether businesses would want to be evaluated on those because that might not align with their own utility.
Yes.
What they care about. And so maybe, jumping ahead here, they get the question, but there is also this issue of like what utility the evaluator cares about versus what utility the evaluated agent cares about.
Absolutely, right. Yeah, and I think the way that often gets modeled in like the econ world is like, yeah, you have these like asymmetric utilities, right? So you look for equilibria between the two. But I think it's absolutely like that's like going to be core to what we analyze, right? Is how do you, given that you have these different players with asymmetric, both information and asymmetric utility, how do you get to a point where what does it look like for information to be revealed in that system, and when might information not be revealed? So thanks for that. That's a good preview of what's coming. So in fact, like specifically the way, like our specific approach to trying to answer this question here, it's not the only approach, but it's just what how we decide to think about it is we give a theoretical model of incentives for an agent to share these kinds of unknown metrics with an evaluator. So here's exactly where we tried to analyze this case where you have these asymmetric incentives and asymmetric information. Okay, so before I get into the details of this model, let me kind of go through a thought exercise to just build some intuition for what is it that we're actually going to try to show here. Okay, so this will be like a group kind of thought exercise. Imagine you are a food delivery courier, and you're working with some app. The app offers you a price for each delivery that you complete, based on like features. So the question I'm going to pose to the room now is, what features would you want or not want the pricing algorithm to account for? So I'm going to I'll say raise your hand. I'm going to show like A, B, and C, like a couple features. I want you to raise your hand if you want it to be accounted for in the pricing algorithm, and keep your hand down if you don't. So, okay, so raise your hand if you want the pricing algorithm to account for whether the restaurant tends to have a super long wait time. Okay, great. Raise your hand if you want the pricing algorithm to account for whether it's raining outside. Okay, and then raise your hand if you want the pricing algorithm to account for whether the recipient is likely to tip generously. Okay, great, interesting. Okay, so actually, yeah, I'm curious. Okay, Yelena, you raised your hand for that one. Yeah, what's the reasoning behind that?
For which one? For C?
Yeah, for C.
I mean, if you're a delivery driver, you rely on tips for your income quite a lot. So of course you would want to know whether the recipient is going to tip generously or not.
Yeah, that's a good point. Yeah, and I think actually this gets to the, okay, that's good. Hold on to that intuition, because that's really nice. Yeah, so this is what my initial intuition was, which is that okay, yeah, which I think is similar if I were to look at the proportion of hands that went up. I think that roughly tracks with where okay, maybe you want that the restaurant, you want it to be accounted for if you have to wait a really long time, that costs your time. But I think what I meant with C was like a binary indicator where it's 1 if the recipient is likely to tip very generously, and then 0 otherwise. But even then,
if I were a deliverer, I would accept lower lower price delivery if I knew that the person I'm bringing food to is going to tip generously, because that makes up.
Yeah, it's a good point, right? So, and it kind of depends on what you expect. Yeah. So, okay, this is going to be very relevant in the model in a second. But in fact, what we're going to show is that depending on where that threshold is of how generously the one will tip, it actually turns, so okay, so a preview of the theoretical results we show are that the agent will prefer to reveal metrics that differentiate very high cost settings from the rest. So something like whether the restaurant tends to have a really, really long good time, and conceal metrics that differentiate very low cost settings from the rest. So this would be a case when, say, I have a binary indicator of whether a recipient is likely to tip generously. That would be like if a recipient is going to tip you like a real, if you're going to like deliver to some very rich person and you know they're likely to tip very generously, then it's an indicator of that, and then 0 the rest of the time, or no information the rest. So yeah, like there's this like moving threshold that will change this result. But indeed, there's going to be some trade-offs that's why you need such a low threshold. Yeah.
The thing I remember reading thing about sort of like gig work for nurses, which is a bigger thing, where in some cases it'll be things like people will be offered lower salaries, lower hourly rates because people go through data brokers and like discover they have debt or something.
Yeah.
And so this is kind of like the second category where it's like you don't want your employer to realize that you less.
Yes.
In the situation, you would rather keep that information secret.
Right. Exactly. Yes. Yeah. That's a great intuition, and I think that's a good example of what's going on here. Another example could be like, if you're, say, driving for a person from point A to point B. If point B is like already really close to your house and you're going that direction anyway, then like you'd be willing to do it for for much lower than probably would be otherwise what the posted price would have otherwise been. Yeah.
And you want to pay the posted price instead of what you actually would accept.
Right. Yeah, exactly. Yeah. That's the right intuition. Yeah. Right. So okay, so now we've built up a little bit of intuition. Let me actually get into the model itself, and then we can formalize this. So what we start with is a standard principal agent game, which is a game from contract theory. Actually, let me just get a show. It's like, who has seen a principal agent game before? Okay, I see. Okay, yeah. Anyone other than previous postdocs in Mike's group? Okay, so then it seems like this is like a fairly new model to folks here. That's cool. I'm gonna start from I'm just gonna give the basics of it, and we'll go through it slowly to just to show the base of where this theory is coming from. So this is what we call principal agent, where it's another way to think of it is it's a sequential game or a stack over game where we have 2 players and they move in sequence. So we start with a principal who, in the previous example, you can think of that as the rideshare app itself, right? Who's setting the prices. And then we have the principal wants the agent to complete some tasks. So the agent here we can think of as the driver in the previous example. And the principal and the agent share a prior over the cost of that the agent will incur in completing the task. So that is going to be given by the random variable C with CDFF. And the way the game proceeds is in the first step, the principal, on knowing this prior over the cost, the principal is going to pick a payment P or offer a payment P to the agent for completing a ride. So they have to decide this before anything else happens. The agent then gets to observe that payment P, and the agent also gets to realize what they're out in the field, they can observe what the actual cost is for the specific ride. And they will now, in the second step of the game, exert effort or complete the ride if the cost that they observe is less than the payment that was offered. So that's if they make money from the transaction. And then finally, if the agent does exert effort and complete the ride, then the principal receives a value B if the ride is completed. Okay, so the equilibrium of this game is actually pretty simple to think about, right? So at equilibrium, we can give the principal's utility and the agent's utility. So the principal's utility here is just simply, or here this is an expected utility. So the principal's utility here is going to be the probability that the agent completes the task. So that's F of P, this F is the CDF here, right? Times the payoff that the principal receives for the completed task, right? So people got value B, they have to pay P, so they get B minus P. On the agent side, it's a really similar thing, right? We're looking at the agent's expected utility as well. So the agent's expected utility is a function of the indicator or the event that the agent completes the task. So that is if C is less than P, times the agent's payoff for the completed task. So that's going to be the agent gets the agent gets P, and they have to. Right. So these are both what happen at the equilibrium. Questions about this model so far? Did that all kind of make sense? Okay, great. Because now we're going to make it more complicated. So what we've done, so this like solution concept. This is like a standard contract theory model. Yes.
So the expectations, CDF, should I think about that as really a distribution over the rides or tasks that then correspond to costs, or like, I'm just trying to I
think that's right. Yes. So you can think of that as like, there's a universe of rides, right. Like I could offer, there's like a universe of what rides could come up in a city in a given day. And so I can think of C as like, I have a price at the beginning of the day, but I don't know what the rides are going to be yet. So this is like C, the distribution over all the rides that could happen.
Right. That makes sense. Thanks.
Great. Yeah. Great question.
Can I ask
Any
a
other
question?
questions about? Oh yeah. Is that coming from Zoom? Cool.
This is Jerry Drew from computer science. I guess I'm considering the situation where, as a principal, if I interact with multiple drivers over time, do I have a notion that I observe like some of them are not completing it, but others are completing it? Therefore, I would be able to update my prior.
Okay, very good question. You're now getting into the field of like online contract design, which is fairly new and also not something that I'm going to address in this paper today. But yes, like people are studying that. I would look up, like online contract design for that.
All right.
It's a great question. Thanks. Today I'm going to only assume like a one-time like a single one-round game. But I think trying to extend, as I describe this model, I think if folks work on online, I think there's like really interesting extensions of this to the online side. Yeah. Okay, cool. Well, feel free to continue to raise your hands if you have questions, because what I'm gonna, yes.
And assume that the shared prior like known to both the agents.
That's right. So this is a shared prior. So both the knows same distribution at the beginning of the day. Great question. Okay, good. So what we're going to add now, because like at the very beginning, we were talking about metrics, unknown unknowns, information transfer. So what we do in this work is we build on top of this base of this principal agent game, which has existed for decades in contract theory, and we add this element where the agent, let's say, knows some additional cost correlated variable. So in our running example, this could be, say, the amount of traffic. So the agent knows that this variable, the amount of traffic, is going to be correlated with how hard it is, how much time it takes them to complete the ride, right? So let's call that random variable X, the amount of traffic at any given time. And what we add now is an additional step in the game where before the rest of the game happens, the agent has the opportunity to choose whether or not to reveal this cost correlated variable to the principal. So what does that look like? Well, if the agent reveals the cost correlated variable X to the principal, then now the principal knows that, well, traffic is relevant to the agent's cost. And so they can now, what it looks like specifically in the rest of the game is they can now like have their payment be conditional on this variable. So instead of just picking a single payment at the beginning of the day, they can have this be this function rho of X, which is, you can think of it very simply like if X is binary, like it's either high traffic or low traffic, then at the second step, the principal gets to offer one payment if it's high traffic, a different payment if it's low traffic. And they don't actually have to know the traffic ahead of time. This is just like what the realized traffic is at the time, right? And then the agent now will complete the task if their realized cost C is less than this rho of X rather than just that original single P. Okay, so actually, yeah. So what we're going to ask now is like the core question that we're going to ask here is, well, when would the agent in this first step of the game, for what types of X will the agent be better off revealing this in the first step? And it turns out that this is actually not that, it's a bit subtle. Like there's some competing incentives for the agent here, some of which Yelena got at in the earlier example. So on one hand, right, this is like the tipping thing that you mentioned. If the feature is revealed, then the agent will get higher compensation at the higher cost setting, right, and be able to complete more tasks. Right, before they wouldn't have been paid enough in the really high traffic settings to even bother doing that, but now that will become possible. Right, the trade-off is that they might get paid less in the low traffic settings. On the other hand, though, if they were to keep this information to themselves, well, because of the way the principal has to set that single price at the beginning, but depending on only the marginal distribution of cost, then they might get paid in lower cost settings, right? They could get away with, like, say the traffic turns out to be really low all day, then, well, principal didn't know that, so they might end up getting paid like a little bit more, right? So, so this core question that we're thinking about then is like, well, then what can we say specifically about this variable X in a bit more formal way that kind of gets at these competing factors here?
I have a clarification question online.
Yeah, of course.
Is X here? What is the agent reporting? Is it the realized value of X, or is it just like, this is the variable you should be measuring, and we're not worried about like agent being untruthful and stuff?
Yeah, great question. Excellent question. So we're assuming that when the agent reveals, we're considering a world where the agent is revealing the full variable. So the agent is not allowed to lie here. The agent is it's like, think of it as like revealing a full feature to somebody who's building a model. We also assume that the principal, being say like an online platform, once they know that a given feature is relevant, we're trying to consider a world where the principal just can verify this and has data for it. So, like, I mean, there's other models out there where you can consider an agent's ability to lie here, but I think because we're trying to think of these like very powerful online platforms, we're considering a world where the agent can't lie about the here. So
okay, so the principal can observe X but not C.
The principal, okay, good question. So the principal doesn't get to observe X yet at the stage of setting the price as P. So I can show, right, so settings of X, right? The principal knows the specific, specifically the principal knows the joint distribution of C and X once the agent reveals X. So
okay,
it's still a like Bayesian situation where like in between this yellow arrow and the first blue arrow, once the agent reveals X, now the principal knows the joint distribution of C and X, and from that they have to determine their payments row of X. That makes sense?
Okay.
So yes, row can condition on X, but the principal doesn't need to know the realization of X in order to set those prices optimally.
Got it.
That makes sense?
Thanks. Yeah.
So the agent like learns the traffic that day and decides whether or not to tell them what the traffic is on that day.
Yes, that's right. So, sorry, no. The agent. Okay, really good question. No. The agent doesn't know what the traffic is. So this is all happening before the day begins. Think of like both of these arrows starting with like before the day starts.
Mm-hmm.
So actually in that first, the agent has to decide whether to give this measure to the principal before they know what the traffic is going to be. So both principal and the agent, sorry, at the very beginning of the day, I have a timeline for this. Let me just show that because I was like, not sure if we, I think this might clarify things a bit. Okay, this, oh no, this is not the right timeline. Did I delete that slide? I hope I didn't. Here, okay. So this is a bit more formal than my previous picture. The black is the standard principal agent game, and the gray is the element that we added. So, okay, so at the beginning of the day, time equals 0, the principal and the agent share their prior over the cost, what the cost could be. And the agent also knows the prior joint distribution of the costs C and X. Okay, so then what happens in the next step is the agent has to decide whether to reveal the observability of X to the principal, and then in doing that, they reveal the joint distribution of C and X to the principal. Then if they do so, at that point, depending on whether the principal is either only working with marginal distribution C or the distribution of C and X, the principal has to design their contract. It can only depend on X if revealed in the previous T equals 1 step. Okay, then at time equals, now the day starts at like T equals 3. So X is actually, you get like, you draw what the actual traffic is for the day. The agent actually learns what their cost is going to be. And then at that point, the agent, now being in the road, gets to decide whether to complete the run. And then finally, that's everybody's utilities are realized at that point. Yes.
So the engineer is really deciding if they would like their cost structure to be based on only the prior on C or the joint prior on C and X, and informs the principle of that.
That's exactly right.
Okay.
Yes. Yes. That's right. Okay. In the interest of time, I'm gonna kind of continue forward to the results. But I think based on what I've been hearing, like it seems like folks have a very solid understanding of the model here. Okay.
Just one quick agent gets to decide that. Why couldn't the principal decide the pricing model? Or is it symmetric in some way?
So it is the principal who decides the prices, but the agent gets to decide.
Yeah, like what, but the principal could say it's going to be based on the joint. Or you're saying they wouldn't have access?
That's right. So we're considering like
keep Google Maps to giving me some instantaneous information on traffic conditions. Okay, got it. So yeah, saying X is only to be shared from the agent.
Yeah, and the reason we do that is like I think we're just trying to come up with like the most tractable model to try to reason about this like fundamental kind of unknown things. So we think of X as like the unknown here, where the principal can't do anything unless the agent says something about it. Yeah, but really good.
Understood. Yep, thanks.
Okay, so now what I want to do now is like given that model, formalize the intuition for that we've been building up to this point about like when would the agent prefer to reveal or conceal. So in order to formalize this, that previous kind of from the previous example, we define a thresholding feature, xt, which is a random variable that is, let's keep it really simple, it's binary, and 0 if the cost C is greater than some threshold, and 1 if the cost C is less than or equal to some threshold. So we can think of this as like, it's a binary feature that's revealing some part of the cost, right? So, so to relate this back to that previous kind of theorem in words, or theory in words, we show that the agent is going to prefer to reveal variables xt for if the threshold t is high enough, for t's that are high enough. So we're going to have some regularity assumptions. I'll talk about those in a second. The cost has to be bounded above by some c bar. And we will also require for the principal's value b to be in some range. And I'm going to talk a bit about that in a second as well. And under these conditions, then there will exist a threshold t lower, such that for all thresholds t greater than t lower, the agent will prefer to reveal xt. So what does it mean for t thresholds t greater than t lower? This means that like there will exist some t lower that's like maybe pretty high up, maybe close to the maximum cost, such that like higher thresholds, like xt's that are that indicate a high cost, are going to be ones that the agent will prefer to reveal. So it's like a sufficient condition for revelation is of this thresholding feature is for that threshold t to be really high. Does this make sense? Okay, Great. Okay, so what are the conditions that I was talking about? Well, the first kind of regularity conditions are fairly kind of standard, straightforward. You know, we have differentiability here. This just makes it easier to analyze. The proofs all involve first order conditions. The second assumption is one that's pretty standard in economics. It's called the monotone reverse hazard rate. You can think of this just as simply log the cavity of the cost distribution. This also makes things easier to analyze from a, this is a pretty common regularity condition when people are analyzing like prices and incentives in economics. It's the dual of the hazard rate, which is also common in statistics if folks have dealt with that. I would think of these two just as both like regularity type conditions. The condition here that's probably a bit that is not so much just a regularity condition, which we need to like talk about a bit more, is this condition that the principal's value needs to be in some range. Okay, so specifically, I would think of this as saying that the principal's value is kind of like in a Goldilocks kind of range where it can't be too high and can't be too low. So imagine that the principal's value for the task being completed is like really, really high. Like they get like, you know, $1 billion from somebody completing a ride or something, right? Then what happens if the principal's value is really high is that at equilibrium, the principal's optimal hidden price, like without information being revealed, is already going to be the upper bound on the agent's cost. So this is like relative to the upper bound of C bar, right? In that case, the agent can only end up with lower prices if they reveal and any additional information, right? So here, there's going to be no world in which you'll have a thresholding feature that will want to be revealed. On the other hand, if the principal's value is really, really low, then it's possible that the principal will not be able to price high enough to accommodate high cost situations, even after information is revealed. And so then it won't be worth it to the agent to reveal information either, right? So what we have here is we do need that the principal's value is kind of in this nice range relative to the agent's maximum cost. And then, you know, from there, then you'll have, and then in all the other cases, you kind of have very like straightforward, it kind of reduces to a very like simple answer for whether the agent reveals or conceals. Yeah.
So this is if the principal adopts like a thresholding pricing model. Is that correct?
No, actually, so this is just it's actually, think of it as like a parameterization of a type of feature that the agent could reveal. So like in general, the agent could technically, like, if we wanted to analyze this problem generally, you could think of any possible X with any possible joint distribution with C, right, for the agent to reveal. What we try to do here is like reduce that down into something that's a bit more track the reason about. So that's why we came up with this like thresholding feature concept. So this is like, I'm only considering
so you're modeling the agent's behavior, saying, okay, if they're larger than a threshold have been reported.
Yes, that's right. Yeah.
So in the C here for the thresholding, is this C the joint with the prior F and X?
The C is the cost. So the C is the cost with CDFF.
Just with F. So there's
yes,
okay.
That's right. Yeah. So we're kind of like we're considering a family of X's that's pretty restrictive here. It's like only the family of X's that exactly threshold C. Yeah. I think there's room to consider more general X's. We just like, I mean, even more general X's, you might have more noise on either side. But yeah, in fact, we will get to some of that one. But yeah, good question. Yes.
It's kind of like C bar plus 1 over F of C bar is kind of strange, right? Like, is there a clear intuition for why that shows up?
Yeah. So in fact, the actual formula is a bit more complicated in the, so there's like an intermediate result for this, and then we kind of simplified it to this like C bar plus 1 over F of C bar. I think you can think of this as, well, you know what, let's talk a bit more after. I don't know if I have like a short answer now, but yeah, this was just like the simplest form we could get it into. Cool. Okay. So let me now let me go on now to the lower end of the spectrum, right? So I promised you 2 parts of a theorem. So the second result we have is that the agent will also prefer, when will the agent prefer to conceal? Well, we have another sufficient condition for that, which is that the agent will prefer to conceal for low thresholds. So, and we have the same first 2 regularity conditions as before, but we're gonna have a different assumption that I'm gonna get to in a second. For this case. And okay, under some conditions, there's going to exist a lower threshold, T upper, such that for all T less than T upper, the agent will actually prefer to conceal these variables xt. So this is more like if you show a variable xt that activates in really low cost settings. Okay, so we have assumptions 1 and 2 are the same as before. We have a new assumption 3 here, which is one of price elasticity, which comes from the concept of price elasticity from economics. Is the intuition here is like, how sensitive is the agent to price? Like, how much do they actually care about? Do they actually care about how much the price changes, or are they kind of happy? So specifically, this quantity price elasticity is the percent change in price over the percent change in effort. Or you can think of it as like, gradient of like d price over d effort. A price elasticity of really simply put, like a price elasticity indicates that doubling the price would mean doubling the probability of task completion or rates of task completion. This, I think, like how we can think of this in this scenario here is what we need here is that the agent's price elasticity is at least 1 at the optimal hidden price. So what this means is like you can sort of think of it intuitively as like the agent cares about price at the point where if no information was revealed, the agent would cares about that price changing. You don't want, if you end up with a case where the agent doesn't care, then this won't matter. Okay, I'm also going to, let me show kind of the proof for this theorem is slightly different from the first, and I'll show just a quick sketch here because it might be like, well, I won't spend too much time on this, but it will show that actually the way to get results in these types of models is maybe not all that different from what we do in optimization already. So specifically, we just define a function, which is the agent's utility difference for a thresholding feature. So it's delta of t is the agent's utility if xt is revealed minus the agent's utility if xt was concealed. We have an intermediate result here where what we, basically what we do is just show that the right partial derivative is negative. And then because this delta t of 0 is also equal to 0, then you get the result above. So it's not really that complicated of a proof structure, but and at the end of the day inside we're just taking derivatives. So it's not that it's interesting. Economics is, maybe there's different models, but the math at the end of the day is not that far off. Okay, so in the interest of time, I'm going to go on here, and we can come back to these details of those theorems if we want. Let me just bring this back around to our original thought exercise. I think we've said this a couple times, right? Revealing whether a restaurant tends to have super long wait time. This is, I was trying to build intuition for this being equivalent to an XT with a really high T, and then I was trying to have the second example be an XT with fairly low T, right? But I think what's the nice thing about these results, to me at least, is that we have something that's maybe fairly intuitive here that we can maybe port into other settings of revealing and concealing metrics. But there's still a big limitation that, or a con of this particular these particular results is that the agent's action space is fairly limited, right? We consider a binary action for the agent. They can either reveal or conceal, and that's it. But in reality, I mean, in online platforms, in real settings, maybe it's not that simple, right? Maybe the agent is allowed to say add some noise. They can't lie, but maybe we're willing to maintain some level of noise, especially given these differentially private mechanisms that exist out there, right, in online systems. So what we next did was extended this model to think about a case where, well, what if the agent can reveal some garbled information? And by garbling, I mean specifically here a randomized mechanism where instead of just revealing X, we've now expanded the agent's action space to have this full, to be able to choose between epsilon, between 0 and 1, where they will give the principal this other random variable y, which is X with probability epsilon, and some noise psi with probability 1 minus epsilon. So why do we do this? Why this particular mechanism? Well, it's a randomized response mechanism. It's common in like survey design, as well as in differential privacy. It's known that this is a locally differentially private mechanism with respect to the information X. So yeah, and the other nice thing about this is now the agent has a lever epsilon, which interpolates between the full revelation setting and the full concealment setting, right? If epsilon is 1, then it's revealed. If epsilon is 0, then it's concealed. Right, and this, the nice thing too is that this like directly relates to differential privacy, and that you have like an algorithm a pricing algorithm that accesses X only by way of this mechanism is O of epsilon differentially private. Yes.
Assuming the second random variable is independent of the cost.
Yes.
Okay.
Yes. Yeah, that's important. Yeah. Okay, so what's cool about this, and I actually like. My favorite part about this analysis of like this additional garbling piece is that we get like some pretty interesting kind of policy implications here. So specific, I'm going to show you that both of the following settings exist. So setting A is one where the agent's optimal garbling utility. So like say the agent gets to, so in the garbling model, right, the agent gets to pick the epsilon first. So the agent will always, we're assuming that the agent being rational gets to know, like figure out what the optimal epsilon is and review with the optimal epsilon. So that's what that epsilon star is there. So we'll know that like garbling of epsilon, that's always gonna be greater than or equal to the agent's utility from either revealing or concealing, right? Because epsilon is, they're gonna pick their favorite epsilon. It's gonna interpolate between those two. But both these settings exist where garbling is actually strictly better than revealing and concealing. And additionally, both internal orderings exist, where you have that garbling is better than revealed, which is better than concealed, and garbling is better than concealed, which is better than revealed. So why is this important? Well, this first setting, let's like talk about the first setting first, where garbling is better than revelation, which is better than concealment. So this first setting is basically showing an example. This means that there exist cases where the agent prefers to add some noise over if they were to reveal the whole feature over if they were to conceal the whole thing. So what that means is that the agent derives utility from adding noise to their data compared to full revelation. And this is like this, what's interesting here is that this kind of, there's been a lot of analysis in the relationship between privacy and utility in these kinds of like data markets out there for, and often like when economists are, or in this like kind of economic analysis of the value of privacy, there's often this trade-off where the agent, say, has some inherent value for their own privacy, like maybe you assign a dollar value to that, and you compare that to like some amount that a company is willing to pay the agent. But what I find really like interesting about this model is that now we've shown an example where even without any inherent value for price, the agent still prefers the privatized setting just simply from the equilibrium of this scale. So I think this like I think this like can imply like an additional kind of further exploration of models like this, where instead of just thinking about somebody's inherent value for privacy, there's like even more reason to consider private connections. Right. I especially, I think one of my favorite findings from this is this like second setting too, though, which I think is even less intuitive than the first setting, where in the second setting, in setting B, the agent prefers garbling over full concealment over full revelation. Okay, so this is a case where if the agent couldn't garble, the information would not be revealed. So what this means is that in such settings, we have Pareto improvement, right? So allowing for garbling results in a strict Pareto improvement for both the principal and the agent. So that is both the principal and the agent will benefit from in the setting if the agent has the chance to garble. So this is saying like if the agent, if such a garbling mechanism exists in a system, and the principal is saying willing to like hold to that, they're willing to promise to like maintain this level of privacy, then the agent is better off doing that garbling over concealing. And if like otherwise they would have just kept the information to themselves. So I think this is like yet another argument for why privatized mechanisms can be useful, at least. Where here we're showing that like just simply looking at like the incentives in this model, the ability for the principal to commit to maintaining a level of privacy will lead to more information being revealed. Okay. Questions about this? I'm gonna like the next thing I'm gonna do is kind of zoom out a bit to like related work. So any questions at this point?
Yeah, one question. Does the agent need to let the principal know epsilon star?
Good question. Yes. Well, yes. So we assume that the agent does let the principal know epsilon star, but in fact, that's not essential to this. It actually doesn't matter. Like this same results go through whether the principal knows epsilon star or not.
Oh, so you mean the principal's pricing function doesn't depend on knowledge of epsilon?
No, the principal's pricing function only depends on the revealed variable y. And like the principal, even knowing epsilon star, like can't back out additional information about x anyway. So like because it's independent noise this way. So yeah, it doesn't actually help
in our model. If the principal knows epsilon star, does it tell something about like other information like the joint CX and so on?
Yeah, no, not in this case. Right, because not here. It doesn't give the principal any kind of advantage. It's because the principal they can't back out X, and they can't, like, even if you consider the principal like knowing the agent's incentives for revealing the epsilon star, right? Maybe if the principal knows that epsilon star is high, then they'll know that the agent had some like X to conceal, right? Like had some informative X. Like it doesn't actually, the principal's optimal is still to just condition on the revealed variable. So it doesn't actually give the principal any advantage here. We can talk more about that offline if you want to. This is something that I thought about I traced out, and it's like, oh, actually, even knowing that, even in a Bayesian sense, knowing like why an agent would reveal certain epsilon, the optimal strategy doesn't change for the principal. But it's a good question. Yeah.
It's about the last sentence that both principal and agent benefit from this.
Yeah.
Initial idea of garbling. I guess this is only for like one principal and one agent cases.
Yes.
Let's say you have like many agents that have different distributions over the utilities and so like that. Do you still think both principal and agent will benefit from this, or eventually it seems like losing game to the principal versus the group of agents? So I'm just trying to see like is that going to hold for agents over?
That's a really good question, and it's something that has been on my like big to-do list of things to think about after this project.
Intuitively, it's going to be worse scenario than the previous one. That to the principal side.
You think so? I would have thought the other way. Yeah. Tell me more why.
Okay, maybe this could be the case. The intuition could completely go the other way around. But just curious what you have thought about it.
I mean, so as like I haven't analyzed that model yet, but I really want to. I think some of the like my guesses would be, or my initial intuition is that actually this would play out more in favor of the principal because agents might start competing with each other to reveal information, right? So you might have like some agents with more, and especially if there's like heterogeneity among agents, then like information might get revealed from some that benefit them, but others. And once the information is out there, it's out there. So process that continues to favor the principal. But I don't know, maybe we can talk more after about what you think like happens on the principal side.
Sounds good.
Yeah. Okay. I'm gonna just kind of I'm gonna go on now and kind of wrap things up, and then we can like come back for more questions in a second. So I'm gonna zoom out really quickly to like, there's a lot of related work in this space. This paper falls in line with, or is like part of a wider literature on information design and Bayesian persuasion. Lots of work there. In fact, our title is like inspired by this original Milgram and Roberts paper, relying on the information of interested parties, in which they analyze like a buyer and a seller and information revelation. But what we tried to do here that differs from what was done in the past is to bring this into a world of first thinking about unknown unknowns, like that's not really a concept that was there before, and also trying to construct a model that we hope might give, is like more closely related to what's happening now with these like large online platforms, a lot of uncertainty, AI systems, etc. There's another literature here that this is related here, which is literature on price discrimination. Lots of like ideas from there that are, you might see, there's like, does the agent want the principal to discriminate in prices or not, right? But what they also haven't thought about there is like this, and in fact is a big open question that has been proposed there is, well, when will the agent prefer to reveal a metric? When will like these measures emerge in the system? So yeah, lots of stuff here. In fact, also different ways that we can apply these results to, or bring in earlier results to analyze, say, the principal's utility, to analyze total welfare. But, and I'm gonna, in the interest of time, kind of skip over this back if we want to. But this doesn't kind of like, there's still so much more to be done, especially now as like, we have these online systems, we have AI systems where the scale is like bigger than ever before. We have types of uncertainty and unknowns that are big, that are like different from what was there in the past and other kinds of like companies and whatnot. And the kind of piece that keeps me up at night is that, hide that, like in these AI systems, we're already relying on the metrics of evaluated agents and other interested parties. For instance, the US AI Safety Institute, in trying to come up with their like research, their testing and evaluation for AI safety, they partner with Anthropic and OpenAI, which, as we know, are companies that also develop these models. There's also like the whole landscape of AI evaluation is also very decentralized, right? So you have like collaborative approaches where people are trying to bring in folks from academia, different industry points to like come up with this AI Illuminate score was a collaborative approach. Folks may be familiar with like LM Arena or Chatbot Arena, which is a community-driven evaluation system where anybody in the world can go up and go on and type in a prompt and rate two models, compare them to each other. And this generates this giant leaderboard, which comes around to having like lots of market power or impact on the decisions of companies. There's another kind of like smaller thing, like little piece here that I'll mention, which is like LLMs as a judge are like also a core part of LLM evaluation, where LLMs are evaluating other LLMs. And if you think that these systems are agentic, then like, then it like starts to be reminiscent of the model that we were just talking about, right? So if there's kind of one like message from this or like kind of through line in my research recently, it's that evaluation here is not a static problem. We have a dynamic multiplayer game with like lots of different actors with different incentives, different information, different abilities, different power. And I've done some, like today we were talking about like how does a regulator discover new metrics, but I think like the really core question that I like would really like to answer and get towards is like, is the evaluation that we're doing actually improving welfare? Like, is the fact that we have all these evaluation systems out there, the metrics that we're collecting and whatnot, like, is that actually doing us all any good? Or is it just, ways for people to continue to like try to measure things and make things look better? I don't know. Another kind of interesting effort I've been working on is this work in partnership with the Google Vulnerability Rewards Program on studying incentives and outcomes in bug bounties, which is like an example of an entity like a company trying to get third party or get information on their own problems, like from others. So that's been happy to talk more about that sometime too. And right, so takeaways from this work again are that like, we can speak to some of this, like I think this points to some power of participatory design. Also, we're able to show that like privacy preserving mechanisms can benefit both the principal and the agent in some cases. But we of course have lots of open questions here, including what about competition between agents, as you brought up, and also this case of like, well, what if like somebody can pay for information? That's not something we've analyzed in this model specifically. But now, I guess we're close to time. So thank you so much. And I would love to answer more of your questions either now or later.
Are there any questions? Okay, I guess there were a lot of questions during the talk. We can 39. I guess I'm collecting. That's